this video, we're going to explore inverses with logarithms in the context of equations and expressions. So we kind of looked at graphs already, and now we're going to think about inverses as expressions and equations. So one property of inverses that we already have explored and know for any function f of x, if it has an inverse function f inverse x, we can say that f of f inverse x is equal to x, and that f inverse of f of x is also equal to x. So a function and its inverse function essentially cancel each other out, and they return exactly whatever we input if we do a composition of the two functions. So let's take a look at this for the example of if we have f of x equals 5 to the x, an exponential function, compared to f inverse x, which would be equal to log base 5 of x. Okay, and we can look at a table of values. So we can say x and f of x. We can check out 0, 1, and 2. Well, 5 to the 0 equals 1. 5 to the first power equals 5. And 5 squared is equal to 25. So we get our values for x and f of x for a few data points. And for f inverse x, well, our inputs should correspond, or we want them to correspond, with the outputs of f of x. So we can choose 1, 5, 25. And log base 5 of 1. Well, 5 to the 0 power is 1. So that must be equal to 0. Log base 5 of 5. 5 to what power is 5? 5 to the first is 5. And log base 5 of 25. 5 to what power is 25? 5 squared. So our tables correlate the x and y to a y and an x. And we can see, using our tables, the effect of taking f of f inverse of x, as we stated up here. So let's put this in a different color. If I want to take f of f inverse of x, it should equal x. But let's take a look. Let's try taking f of f inverse of 5. So we start with our inner function, f inverse of 5, and we input 5 into that function, and we get an output of 1. So f inverse of 5 is equal to 1. So now we must take f of 1. We can look to our table, and we see f of 1 is equal to 5. So f of f inverse of x was equal to x, f inverse of 5. And if we take f of f inverse of 5, we get 5. We get exactly out whatever we put in. And that makes sense. We can look at this for the other type of example as well. So we had f of f inverse x. And let's do some green. We can also take f inverse of f of x. So let's try f inverse of f of 2 and see what happens. We start with the inner part of our function, f of 2. So I put 2 into my original function, f, and I get out 25. So f of 2 is equal to 25. And then I take f inverse of 25. So I plug in 25 to my f inverse function, and I get an output of 2. So f inverse of f of 2 equals 2. And f inverse of f of x will always be x. So we demonstrate that this property holds with exponential functions and logarithmic functions, and that they essentially cancel each other out. Okay, so now let's take a look at some properties or some forms that we might see this in the problems that we do. So if I have 5 raised to the power of log base 5 of x, this is going to equal x, so long as, well, actually we don't even need to think about our functions. So what we have here is 5 is being raised to some power, right? And if we zoom in on what it's being raised to, log base 5 of x is essentially saying this is the number. It represents the number that you must raise 5 to get, oops, my apologies there, not sure why that's happening, to get x. Okay, so log base 5 of x represents the number that you must raise 5 to get x. And so if we raise 5 to the number that you must raise 5 to get x, of course we are going to get x. Okay, let's take an example here. So let's say 5 raised to log base 5, and we'll say of 25. What would that equal? Well, the answer is it's sort of a shortcut. It's just going to equal 25. But why? Well, log base 5 of 25 represents, this quantity just represents a number. The number that you must raise 5 to get 25. And so if that's what that quantity is, and we raise 5 to that number, whatever number it is that needs us to get to 25, it must equal 25. And we don't even have to do the math. We just know if we raise 5 to the number that you must raise 5 to get 25, it must be 25. Okay, so that is one of our properties of logs. We can generalize it by saying b raised to the power of log base b of x equals x. So this is a key property of logarithms. It is an inverse property. Inverse property. Okay, b raised to the log base b of x gives us x, and that's why. Okay, and then we have a second property. So let's cut this here. If we have, for example, log base 5 of 5 to the power of x, it's equal to x. Because what does this mean? Well, we're saying 5 to what power would have to equal 5x, right? Log base 5 of 5x is like saying 5 to what power equals 5x, or 5 to the x. Well, 5 to the x equals 5x. Okay, let's look at an example. Log base 5 of 5 squared. Well, log base 5 of 5 squared is saying 5 to what power equals 5 squared. And of course, 5 squared, 5 to the second power. So log base 5 of 5 squared is 2. And we generalize this for our second property. Log base b of b to the x equals x. And that is our second inverse property of logs. So those are two important properties. And you want to know, why do those properties occur? And it's exactly for these reasons I outline here. It's basically we're saying raise b to the power that you need to raise b to get x, or b to what power equals b to the power of x. It's sort of redundant in a way. Okay. All right, let's look at a couple examples and then we will wrap up. So example 1, we're going to say 6 to the power of log base 6 of 2. And this has to be equal to what? Well, this part, log base 6 of 2, is saying 6 to what power equals 2. And the logarithm represents that power, or that number. 6 to what number is equal to 2? And then we raise 6 to whatever number you have to raise 6 to get 2. So the answer is 2. Okay, let's take a look at another example. Let's say we have log base 7 of 7 to the third? Well, that simply equals 3, because we're saying 7 to what power equals 7 to the third? Well, of course, 3 is that number. 7 to the third power equals 7 to the third. Okay. What if we have log of 10 squared? Well, this is simply equal to 2, because log implies log base 10. If we don't write it, usually we're implying log base 10. So we're saying 10 to what power equals 10 squared? And of course, 10 to the second must be. Okay, let's look at another one like that. If we have 10 to the power of log 5, well, again, this is going to equal 5 because log of 5 is actually log base 10 of 5. 10 is our default base for logarithms, so we don't always write it if we just write log. And we're saying 10 to, this quantity represents whatever number you have to raise 10 to get 5. So if we raise 10 to that amount, of course we are going to get 5. And 2 more examples. What if we have the natural log, ln, of e to the fourth? Well, this is equal to 4 because ln e to the fourth, the natural log is just equivalent to log base e. And it's just such a common one that we use, we call it natural log, or ln. Just like e is considered our natural base, well, if we say ln, it's implied that it is log base e. And then we're saying e to what power is equal to e to the fourth? Well, of course, the answer there is 4. Last example, e to the ln 7. This is going to equal 7 because ln 7 is equivalent to log base e. The natural log, the natural base, has to be e. So e to the log base e of 7. Remembering that this quantity represents the number that we must raise e to get 7. And if we raise e to that number, you better believe we are going to get 7. Okay, so that is a summary of inverses and logarithms and how we can use them in some